everyone. Welcome to the electromagnetic theory and interference course. In this session, we will discuss about wave propagation in lossy dielectric. So, this lossy dielectric material is a medium in which electromagnetic wave, as it propagates, it loses its power because of the imperfect nature of the dielectric material. So if we understand the wave behavior in the lossy dielectric medium, we can derive easily the other cases like wave propagation in lossless good conductor as well as free space. So let us derive the wave equations in lossy dielectric. Lossy dielectric I can otherwise called as a partially conducting medium because it's not perfect uh, dielectric. It is the imperfect dielectric, or I can say imperfect conductor, where the conductivity is there. Okay, it's not equal to zero. As we compare with the lossless dielectric, where the conductivity is equal to zero, because it's not a perfect. It's a perfect or a good dielectric. There will be no conductivity. We are going to consider a medium. Where it's a linear, isotropic, homogeneous, and lossy dielectric medium. What is the meaning of a linear medium? So for the variations in input, the output changes linearly, right? Isotropic medium is the one permittivity and permeability are same in all the directions. Homogeneous medium means density of the medium or the refractive index, everything will be same at every point. Okay, and lossy dielectric medium means it's a partially conducting medium. It's not a perfect dielectric or a perfect conductor. There will be a little conductivity there. And we are going to consider a charge free medium also, which so volume charge density is zero. So we are assuming and suppress the time factor e power j omega t. The Maxwell equation we know in time varying, time harmonic form, right? That we are going to replace all the four equations in terms of E and H, that is electric field and magnetic field intensity. We already know del dot ds is equal to rho vs. Here rho v is 0, and we know the relation between d and E, right? D equal to epsilon E. From that, del dot es is equal to 0. Del dot bs is already 0. We know the relation b equal to mu into h. From that, del dot hs is 0, and rest here also del cross es is equal to minus j omega instead of ps mu hs. Similarly for del cross hs, js is nothing but sigma es, right, plus j omega. In ds I can replace by epsilon es, right? So these are the four set of Maxwell equations in terms of E and H for the time harmonic form. We are going to take the third equation, that is Faraday's law, and take a curl on both sides. Del cross Es is equal to minus j omega mu is constant. So I am taking curl of the magnetic field intensity. So if we apply the vector identity, that is curl of a vector is gradient of divergence of a vector del of del dot A minus Laplacians of the same vector. So if I apply this identity over here, over this term, okay, del of del dot es will come minus del square es will be there, and instead of j in this minus j omega mu, instead of del cross hs, I'm going to apply the fourth equation, sigma plus j omega epsilon es. So the complete equation is going to turn out to be in terms of electric field. We already know from this first equation del dot es is 0, so that is cancelled, and we can write here del square es, and this is going to be a constant. I am going to take to the right hand side, so minus left hand side minus gamma square es is equal to 0. So the gamma square is nothing but, as we saw, it is j omega mu into sigma plus j omega epsilon, right? And this the gamma is a propagation constant, okay? And similarly, I can write for the magnetic field also. Del square Hs minus gamma square Hs is equal to 0. These two equations are called homogeneous vector Helmholtz equation, or vector wave equations. Okay. And in Cartesian coordinates, we have to understand that each of the each equation it is equivalent to three scalar wave equations. For one for each component of electric field has component along x-axis, y-axis, and z, right? So each will have three, right? So, and we So the propagation constant gamma is a complex quantity as we saw here. So we are going to assume that as alpha plus j beta. Okay, and we are going to find the value of alpha and beta separately now. For that, we are going to take the real part of this gamma square, right? What is gamma square? It is alpha plus j beta the whole square, right? If we take a plus b the whole square, we know that it is equal to a square plus b square plus 2ab, right? If we apply here, it is alpha square. For b square, it will come minus beta square plus 2j alpha beta, right? And from here, we can know that it is equal, real part is going to be equal to alpha square minus beta square, but we are going to take negative of real part, so beta square minus alpha square. So if we equate the right hand side part to here, it is going, what is the real part here? This is a imaginary. If I multiply both the j terms, right, if we get minus 1, so it is equal to minus omega square mu epsilon. Okay, and already we have taken the negative of the real part, right? So this beta square minus alpha square is going to be this term. When I want to take magnitude of this term, general magnitude of a complex number, we take alpha square, root of alpha square plus beta square only we will take, right? And magnitude of gamma is alpha square plus beta square. Magnitude of gamma square means that is going to be the square of it. So if we take that and equate it to this particular same term, okay, same, take the magnitude of this gamma square, what will come? Omega mu. Okay, it will be there as it is if we take the modulus of it. And if you want to take here modulus, we have to take again one root, sigma square plus omega square epsilon square, we will get it. So we are going to uh, all these two equations to find alpha and beta. So if you compare these two equations, if you add it, the alpha square get cancelled, we get 2 beta square, that is equal to this omega square mu epsilon plus this term on the right hand side. So I want to take beta, means what should I do? I should take square root of the entire term. Inside I should take half, and this entire term I am replacing only the second term. For what I'm going to do, I'm going to make the inner part to 1 plus. Okay, for that what should I do? To get, and I'm going to write sigma by omega epsilon the whole square. That term I'm going to write. For that what should I do? I should take this omega epsilon, right? Omega epsilon outside. If I take outside this root, it will be omega, already one omega is there, omega square epsilon I have taken. So here I'm going to write in a different way so that I can take this omega square out of the root, means I'll get this omega out, and here it's going to be mu epsilon I'm going to take as common from these two terms. So mu epsilon by 2 into root of 1 plus sigma by omega epsilon the whole square, outside the inner root plus 1, but it will be within the larger root. And for alpha, if you do it in the same way, we will get the same expression. Only changes here it's plus 1, here it will be minus 1 for alpha. Hope you understood how we found, starting from the derivation of vector Helmholtz equation, and finding that constant, complex propagation constant alpha and beta. We will see the physical meaning of alpha and beta in the upcoming sessions. Thank you, everyone.